Good evening, everybody. Welcome to the East Midlands Centre of the Royal Meteorological Society. My name's Professor Michael Stephen. I'm chairman of the East Midlands Centre of the Society. The Society's mission is to strengthen the science of weather and climate and to raise public awareness of atmospheric science. Local centres, such as the East Midlands, exist to bring the Royal Meteorological Society to its members in the region and to broaden interest among the public at large. We also try, when appropriate, to promote local expertise in atmospheric science. I have a few housekeeping items to mention. First of all, we encourage you to ask questions. Can we have the next slide, please? Yeah. The way to do that is to click on the Q&A button on your screen and type in your question. The questions are then collated and I will read out a selection at the end. We also encourage you to engage further with the Royal Meteorological Society. If you're not already a member, you can sign up for an online general interest newsletter called Met Matters, which is entirely free. For even deeper engagement, you can join the Society, but I'm afraid that's not free. For further details on any of this, please see the Royal Meteorological Society website, rmets.org. It now falls on me to introduce tonight's speakers. We have a double act. Our speakers are Rachel Perks and Jennifer Weeks. Rachel is a senior marine scientist with the Meteorological Office with a long-term interest in marine environment. She has experience working across both public and private sectors. She uses climate models to research changing sea levels and storm surges and how they affect coastal risk. And she has worked on a variety of global and national projects for customers, including government bodies, developers, insurers, reinsurers, and various charities. She's assisted in the Thames Estuary 10-year review and published a tool to enable consultants to assess sea level projections across the globe. Jennifer Weeks is a climate scientist in the Sea Level Group at the Met Office and doing a PhD at the University of Bristol. She has experience generating local sea level projections for different regions of the world, facilitating training workshops and webinars for coastal decision makers in South Asia, and has looked at improving sea level projections for use in coastal impact, vulnerability, and adaptation planning, including working with partners to build coastal resilience to sea level rise in Pakistan, and looking at the UK's high-end sea level rise scenario and how it can be improved. So those are our speakers, and without further ado, I will disappear and
That's brilliant. Thank you so much for that lovely introduction, Michael. So Jenny and I are going to do a double act today, and we're very excited to be here and to talk with you all on sea level rise, projections, and future coastal impacts. So if we could move to the first slide, please, Jenny. Jenny's going to take control of the slides today. I thought it would be a good starting point for all of us to talk about why we need climate change projections. So the three key reasons here are the changing hazard. So as we move into a future climate, we're looking at global sea level rise, but also regional changes in different parts of the globe. And these also impact on the local extremes that we see around our coastlines. In addition to that, climate projections are really useful to help us decide which mitigation choices we might make. So to understand the consequences of the amount of emissions we put into the atmosphere and the different pathways that we might follow in a future climate. And then regardless of those mitigation decisions, the adaptation options that we might look to implement, and those that we really do need in addition. So thinking about things like the Thames Barrier, but also supporting lots of local and national scale risk assessments and adaptation planning. So next slide, please, Jenny. Brilliant. So before we move into how we look at creating sea level projections, I thought we'd go through what we've termed the sea level jigsaw puzzle, and this goes through all of the different processes that we need in order to understand those future projections. So we start here with thermal expansion on the top left. And I think if we move on one slide, we have a really nice animation that talks this through for us. So as the atmosphere and the oceans are warming, this essentially translates through into the water expanding and the sea levels rising. And then in the bottom left, we have ice sheets. So if we move on to the next slide. As I'm sure most of us on the call are aware, with the rising temperatures that we're seeing because of climate change, these are melting ice sheets across the globe, so the Greenland ice sheet and the Antarctic ice sheet. And this is contributing additional water into our oceans and causing sea levels to rise. This same process also affects glaciers, which is the top right of our jigsaw piece here. And then we also have essentially an opposite effect here from land water storage. So as we're building reservoirs and dams on our lands, we're reducing the amount of water that might enter the ocean through our river systems. But this process is much smaller in comparison to the addition from the glaciers and the ice sheets. But altogether, this is feeding into global sea level rise. So next slide, thank you, Jenny. Sorry, preempted me there. But importantly, sea levels are not changing uniformly. So at the top left here, we've got ocean circulation and density. So as the patterns of circulation change in our oceans and as our density is changing, this is also affecting local changes to the sea surface height. And then in the bottom left here, we have contemporary gravitational, rotational, and deformational effects, or what we like to term GRD in the sea level community. So as I mentioned, globally, we're reducing ice sheets and contributing mass into the ocean. But these ice sheets, when they exist, have a gravitational pull that pulls water towards them in this regional space. So as they're reducing and melting, that gravitational pull no longer exists. And we have what's called a near field decrease and a far field increase. So the coastlines around Greenland are essentially experiencing a slight decrease in the sea level relative to the land, whereas the opposite side of the globe to Greenland will be experiencing a slight increase. The next component that feeds into our sea level projections is glacial isostatic adjustment. This is one that I'm sure many of us are aware of from our geography lessons at school. But essentially, as the prehistoric ice ages, the really old ones, have melted off the Earth, the land is rebounding in that position. So the ice sheets that were all over Canada and North America, they don't exist anymore, but the solid Earth underneath them is moving back into its original position. And that's a really long, a really slow process. And then finally, we have vertical land movement as well. So this very much links into having our big megacities around the coasts and having land subsidence. So having additional weight on the land, the groundwater underneath, all resulting in regional changes in our sea level. So if we just move on to the next slide. We have a really nice example here of the tide gauges that we have in Southeast Asia. So on the left-hand side here, we have Manila, which is in the Philippines. And on the right-hand side, we have Bangkok in Thailand. So here we're looking at the sea surface height in millimeters. And you can see from around 1960, both locations are looking at an increase in sea level. But this is very much linked to the subsistence of the land because of the megacities that have developed in those regions. So there's lots of different components here that all feed into the sea level projections that we need to be aware of. And then if we go on to the next slide,
Cool, thanks,
I'm going to
Rachel.
pass over to Jenny to talk through how we create those projections.
Thanks, Rachel. Yeah, so there's kind of various methods that we use to project sea level change into the future. So I'll just outline some key ones here that have been used in more of the recent literature. So first we have process-based projections. So these sum up the individual modelled components of sea level change. So modelling those components that Rachel showed at the global levels and kind of summing them up. So how this works is global climate models are forced with greenhouse gas emission scenarios. Some components like thermal expansion, you can kind of get directly from the models, but others, say typically the ice melt components, they're typically calculated using separate models, but still using driving data from the climate models. In the future, with kind of climate models evolving, these might all be kind of simulated together. There's also an increasing use of more simple climate models or emulators being used to generate future sea level change. And their lower computational cost means that we can generate these projections further into the future, so beyond the 21st century. And then we have kind of expert elicitation methods, where the projections are based on responses of experts in sea level change. And this is quite a useful method, which is used for, say, kind of long-term ice sheet responses, which are deeply uncertain. Yeah, in terms of kind of studies of local sea level projections, so kind of moving from the global to the local scale, there's various studies which have generated local sea level projections. So I've outlined here some key ones that we're going to talk about in the rest of this talk. So this includes the UK climate projections released in 2009 and the more recent UK climate projections published in 2018. So that's UK CP09 and UK CP18. And then there's also more recently the Intergovernmental Panel on Climate Change's Sixth Assessment Report, which was released in 2021. So they also released local sea level projections for across the world, including the UK. And then IPCC actually teamed up with NASA to produce an interactive portal where people can explore these local projections for coastal locations across the world. So within these studies, they typically present sea level projections as the as a range. So typically it's the IPCC likely range. And what the likely range is, it characterizes the central 2/3 of the underlying probability distribution. So they're typically presented so as like the 5th to 95th percentile range. That's what was presented in UK CP18, for example. So if we look a bit more into the UK CP18 sea level projections that were presented to 2100, what UK CP18 found is that sea levels across the UK are expected to continue rising under all scenarios. Under the lowest emission scenario, so RCP 2.6, we were typically seeing at the lower bound around a 20 centimetre increase at 2100. And then when we look towards the upper bound of the highest emission scenario, so that's RCP 8.5, we're typically seeing around a metre at 2100. And due to the effects of glacier ice-static adjustment and Greenland ice sheet, the kind of spatial effects that they have on the UK, this means that we see higher sea level rise to the south of the UK compared to the north, where we see relatively lower sea level rise. The data for UK CP18 is available publicly and online, these sea level projections. So, for example, in the Climate Data Portal or the UK CP user interface. Oh, yeah. So UK CP also published some exploratory extended projections, which are available to 2300, and that's using the emulator methodology, so slightly different. So these are considered to have lower confidence compared to the 2100 projections. And so it might not be immediately obvious why we might need kind of projections extending this far into the future. However, there are actually many cases where these projections might be used in kind of different decision-making contexts. So, for example, in flood risk assessments, there's a requirement to plan for 100 years into the future, and that already pushes out to 2125. Or, for example, nuclear facility planners, they have to take into account sea level rise for the whole lifetime of the nuclear facility. So that includes operation and decommissioning, so around 160 years or longer. But kind of projecting out to kind of beyond 2100 and kind of across centuries also gives an indication of the committed sea level rise. So certain components such as kind of the kind of timescales of the oceans to absorb heat, and also the timescales of the kind of ice to react to warming, they're quite long, and that means that we'll continue to see sea levels rising even if greenhouse gas concentrations are stabilised. So after the IPCC's 6th assessment report was released, we looked at how their local sea level projections compare with global and local sea level projections compare with UK CP18's sea level projections. So what we can see in this graph is the sea level projections at the global on the left and local scales for London on the right. The kind of shaded bands from around 2020 to 2150, they're showing the IPCC 6th assessment report projections under low emission scenarios and high emission scenarios. And then we've kind of compared them with UK CP18, which are the bars that you can see at 2150. And what these graphs are showing is that actually, despite the methodological and model advances in IPCC's 6th assessment report, actually the projections are broadly similar at 2150. And this is kind of indicating that the kind of projection science has stabilized a bit. And the actual overall kind of hazard profile between these two sets of projections hasn't substantially changed. Okay, I'll pass over to you again, Rachel.
Brilliant, thanks, Jenny. So a couple of years ago, Jenny and I worked together on pulling through all of these methodologies to develop a sea level tool, and Jenny came up with the great acronym PROFSEA, which stands for Projecting Future Sea Levels. So the tool we've developed can generate these local sea level projections all across the globe. So you can see an example here on the right hand side that ranges from projections in Auckland, in New Zealand, all the way through Asia, through Europe, and across through to America. These projections can be generated out to 2100 using that standard method that Jenny was talking about, but also out to 2300 as well using the different methodologies. So I think here is a really nice example of looking at those regional variations. So whilst you can see that many of the plots are looking at sea level projections rising in a future climate, I draw your attention to Barentsburg on the top row, which is actually showing a potential decrease in sea levels. And again, this is due to the proximity of this one to the Greenland ice sheet and those processes that we were talking about earlier. So if we can move on to the next slide, the next few slides we've got are all about the different projects that we have ongoing at the Met Office. Some of them are finished and published, and some of them are sort of currently underway. And this is one that is currently underway. So this is the Advancing Arctic Capabilities Programme. So the Met Office was tasked by central government to investigate how sea level is changing in the Arctic region, with an intention of aiding military planners as well as like the shipping industry to support their future operations. So one of the key aspects of this work was looking at sea level projections. And I've recreated the plot here for Barentsburg, but also shown an example here from Vankaram, which is just off the coast of Russia, to show the sheer differences between what these sea level projections will look like in a future climate and the implications this has for shipping. So it could mean that docks become dry in a future climate, but it could also mean that docks are sort of overrun with excess water and therefore have significant impacts from the local extremes. If we can move on to the next slide. We have another example here from South Africa. So this was part of the Weather and Climate Service Partnerships. So the key goal of this project was to inform actions around policy to reduce risk and safeguard lives and livelihoods. So whilst these projects cover a huge range of different sort of climate factors and weather factors, we're focusing in on sea level again. And you can see the plots on the right-hand side for Durban and Simons Bay, which show likely increases in sea level in a future climate out to the end of this century, and showing that under these higher emission pathways, or RCP 8.5, the increase is going to be substantially more than under those lower emissions pathways. And then if we can move on to the next slide. And then another example here we have is from the ARC program. So the aim of this project was to deliver new technologies and innovations to deliver climate information and advice to vulnerable groups across the globe. So you can see the map on the bottom right here of the different regions that the team were looking at and developing sea level projections for. But here, one of the key takeaway messages from this work was looking at the different components that fed into the sea level projections. So here they found that the thermal expansion component is a leading driver of change, but the groundwater extraction actually on the subcontinent has a significant impact on the sea level projections that we see here. So depending on where we are in the world depends on how large the different factors are contributing to the overall change in sea level. So if we could move on to the next slide. Taking a slight sort of change in track now to look at local variability for a moment. So we've discussed through the jigsaw puzzle for looking at global sea level rise. We've also discussed the jigsaw puzzle for looking at regional changes in sea level projections. And the final part of this jigsaw is looking at local variability and extreme sea levels. So this is combining the mean sea level, what we've got already from our tide gauges, but then along with the tidal cycle, the storm surges that we might see and waves, both generated from sort of severe storms, either in the location that we're looking at or a long way away. So if we can move on to the next slide, thank you. So thinking about these extremes, combining the mean sea level with the tides and the storm surge, some work I did quite a few years ago now was looking at essentially characterizing extreme sea levels in the present climate, and then thinking about how sea level rise might change these extremes in a future climate. So I pulled out an example here that we have for Immingham, but we actually have these results for all around the UK coastline at a roughly 2-kilometre grid spacing. And you can see the black dash line at the bottom here is roughly talking about what we might expect for like a 1 in 1 year event, all the way out to a 1 in 10,000 year event, very much based on Environment Agency baseline data. So if I pull out the 1 in 100 year event as an example, an extreme sea level is roughly 4.9 meters. So we might expect that to have a problem for Immingham currently. But when we look to apply the sea level projections, we're looking that that 1 in 100 year event will increase to 5.3 meters under a low emissions scenario, or 5.6 meters under a higher emissions scenario, all having significant implications for sort of flood defense options as well. So if we could move on to the next slide. So one of the other bits of research work that we've been doing within the Met Office is very much focused on coastal resilience. So trying to pull all of these factors together, pulling together the sea level projections, pulling together the storm surges and the waves, and thinking about flood risk without looking at actually modelling that flood risk. So we're looking at proxies. So to go through this work, this is something I'd normally spend a full hour on, but I've tried to streamline it into 2 slides. I've gone for a case study approach. So back on 6th of December 2013, Storm Xavier created one of the biggest coastal flood events in the UK for a significant period in time, so since about 1953. So it's had significant impacts all along the east coast of the UK, with houses falling into the sea because of increased coastal erosion, significant amounts of flooding, and huge impacts on businesses and livelihoods. So in the UK, we have produced a set of 30 daily weather patterns. And what we were able to do with this work is link that particular storm to one particular weather pattern, which you can see here on the slide. So this is essentially a low pressure system over the North Sea and Scandinavia. And this leads to a high storm surge risk on the East Coast, which is what we saw. And then the final part of this coastal resilience demonstrator project to look at this particular storm was to look at how our daily maximum skew surges link to those weather patterns. So it was known to the forecasters at the time that this weather pattern was coming for the UK. It was forecast, and these weather patterns are linked to storm surges. And as you can see on the plot on the right-hand side, there's a 2.7% chance that the daily maximum skew surge was going to exceed the warning threshold that we have. So we already knew that this weather pattern had potential to cause significant flooding around the UK. But a large part of this work was to look at how this might change in a future climate. So if we could move on to the next slide. So what we did here was we looked at sea level projections out to 2050, and we recompleted the assessment. So on the right-hand side, you can see the stacked bar charts here. And instead of having a scale of sort of 0 to 3%, we now have a scale of 0 to 60%. So I think, Jenny, if you click, there might be a little bit more text that fills in on this slide, hopefully. But if that doesn't come, that's okay. I can talk through it regardless. So we're looking at the projections out to 2050, but we also look at projections out to the end of the century. Oh, there we go. And what we can see is that for that same weather pattern 14, the exceedance probability increases to more than 8% in 2050, and it increases to over 50% by the end of the century. So a significant increase in the potential for risk of flooding from this weather pattern. Now, alternative way of looking at this is in the present climate, there are only 2 weather patterns that would be considered risky for Immingham, and that the forecasters would consider as important for warning emergency responders, warning the Environment Agency, so that they might go out and put demountable defences up. But when we account for sea level projections to 2050, the number of weather patterns actually increases to 8. So that's changing the amount of work that our forecasters and our emergency responders will have to do from 2 to 8. And by the end of the century, it actually increases to 29. So there's actually only 1 weather pattern that we wouldn't consider a risk because of the sheer increase in the amount of sea level that we have. So the demonstration here is very much based on storm surges and combining that with sea level. But we've also looked at the comparison for waves, but I haven't shown that here. And we've also looked at how the weather patterns themselves are changing in a future climate. So I think I'm handing back to you, Jenny, for the next slide.
Cool, thanks, Rachel. Yeah, so as I mentioned before, so far with the sea level projections, we've typically been talking about the likely range, so that kind of central 2/3 of the distribution. However, There's also kind of several processes which could lead to sea level rise above the likely range, but they're characterized by what we call deep uncertainty. This kind of area is also kind of typically referred to as the tail risk, but in sea level science, we call it the high end. So yeah, it's quite kind of a fast kind of evolving area of science. So what is kind of high-end sea level rise? Antarctica, for example, has the potential to contribute a significant amount of sea level rise to the UK. However, it also has the greatest uncertainty in projections. So in particular, the processes of marine ice sheet instability and marine ice cliff instability can cause kind of self-sustaining and rapid loss of ice. And this can kind of lead to accelerated sea level rise. So there's kind of some diagrams here of how they work. Just briefly, marine ice sheet instability can occur when the ice sits on kind of a downward sloping bedrock. And as the ice retreats, it reveals kind of a greater ice thickness, which increases the flow of ice. And then marine ice cliff instability can occur when ice cliffs above a threshold subaerial height are exposed and they are structurally unstable and then collapse, revealing even higher cliffs, which then subsequently collapse. So they're kind of such kind of a tipping point processes that could occur in Antarctica, which could cause significant sea level rise to the UK. Since, as we mentioned, the Greenland ice sheet is close to the UK, it doesn't actually then cause a significant amount of sea level rise to the UK. However, the melt from Greenland ice sheet causes the kind of a weakening in the Atlantic meridional overturning circulation, and this is linked to dynamic sea level changes. So actually there are kind of also these tipping point mechanisms in the Greenland ice sheet, which actually could have relevance for the UK as well, even though due to that proximity, there's not kind of substantial scaling factor in terms of the amount of sea level rise. In the UK, we refer to the high-end sea level rise as high plus plus or H plus plus. So in the UK, we call it the H plus plus scenario. So what is high plus plus? So this it focuses on the sea level rise hazard. So that's kind of a bit separate from low likelihood, high impact scenarios. The H++ scenario in the UK was originally developed for dynamic adaptive pathways planning under the Thames Estuary 2100 plan, and that involved a kind of structured expert judgment approach. So one of those methods that I mentioned earlier. It was then revised under the UK climate projections in 2009. And so what the scenario actually is, it's a single range at 2095 of 0.3 meters to 1.9 meters. In practice, actually, what may be used in, for example, in Environment Agency regulatory requirements is that upper bound of 1.9 meters. And then when, at the time of kind of UK CP18 development, there's kind of deemed insufficient evidence for a major update of H++. So this H++ scenario, the range at 2095, that's still what kind of a lot of guidance in the UK for coastal planning uses at the moment. So kind of example use cases are, say, like as I mentioned before, nuclear facility planning, and also the Thames Estuary 2100 plan mentioned here. So effectively cases where you have to have risk-averse decision-making and you really have to prepare against the worst potential sea level rise, even though it may have what we associate with lower confidence. So yeah, just kind of saying a bit more about the Thames Estuary 2100 plan. So this is a good example where sea level information in the UK is used. So an example which uses our sea level projections. So they actually take an adaptive pathways approach to managing future tidal risk. What they have is a range of options. So that combines the kind of short-term low regret interventions, which buy time, with longer-term options. So for example, that can range from raising defences to actually having new barriers and actually eventually a new barrage as well. The pathways kind of have a series of decision points with intervention milestones. And as you can see kind of by one of the red dotted lines, the H++ scenario forms a key part of the decision-making process in the Thames Estuary 2100 plan. So an increasingly popular way of trying to represent this high-end sea level rise space is through using storylines. So we can use this approach to kind of explore and communicate this deep uncertainty in the future climate response. So storylines are they're effectively, in this case, being used as just kind of a single trajectory of future sea level rise, which are physically based, and they describe a plausible future pathway. So we're kind of just looking at trying to build a single time series, which can then be used to kind of explore what if in kind of coastal planning and decision making. So an example of a high-end storyline is in the IPCC's 6th assessment report. So this is kind of similar diagram to before, but I've added a comparison of the high-end estimates in IPCC AR6, and I've plotted in the right plot the UK CP09's H++ scenario. And what we can see actually, if we look at that comparison on the right between the UK CP09 H++ scenario and the IPCC 6th assessment report, we can see that actually these two high-end scenarios, they are still compatible. The AR6 storyline does cross over, but actually beyond 2100, this AR6 storyline, it does actually rapidly accelerate, and that's due to the incorporation of marine ice cliff instability modelling, which kind of came about after the release of UK CP18, and that AR6 was able to include. And what this kind of comparison shows is that actually the existing H++ kind of needs an update because there's been new information that's been provided due to kind of the advances in methods and models. If I go on to the next slide. Yeah, and the UK CP H++ scenario and the AR6 storyline, high impact storyline, they're not the only high-end sea level estimates. There's actually kind of, as I said, it's kind of a rapidly developing area. There's quite a few different studies which have looked at producing high-end estimates tailored to kind of risk-averse decision making, and kind of exploring a wider range of different sea level rise futures. So some work that we've been doing at the Met Office is looking at generating storylines of future mean sea level rise that are consistent with the UK CP18 methods. What we've been doing is we've been working with the Environment Agency. The Environment Agency are kind of a super user of UK sea level projections. They use the projections kind of in widespread guidance for England. And then that's kind of then subsequently used by people making decisions. So they kind of outlined a series of requirements for kind of future sea level rise information. So they wanted sea level information that could span the whole scenario space, so not just high-end sea level rise information, but something that's kind of consistent across the whole distribution. They want the ability to explore what if scenarios. So what if we see this ice sheet instability mechanism? They want the ability to explore sea level rise in terms of warming levels and also rates, which might be a more useful metric for some decisions. And they also were interested in information spanning beyond the 21st century and actually kind of on the century timescale. So what the figure on the right is showing is this new storylines approach. It's actually a kind of a framework that's been developed where you can kind of select different time series from the same UK CP18 projections. So what we can see here is 5 storylines, 3 kind of encompassing the IPCC's likely range, that's story A, B, and C, and then 2 kind of high-end storylines which are tuned to different high-end estimates, so the ones that I presented and that are available in the literature before. But it's a flexible framework, so any other kind of high-end estimates that are published in the future, we can then kind of generate storylines tailored to those high-end estimates. And this means that information can be tuned to different risk tolerances. We've actually been using these storylines to explore sea level rise and how it affects decision-making processes. So this is kind of an example here. We ran a decision gaming workshop. So this is effectively kind of stress testing decisions across kind of a long time scale. So what this involved is we came up with a hypothetical location, and this is actually somewhere along the east coast of the UK. We generated a visual aid using AI, which is what you can see on the left. So we kind of came up with this location that was a port city of around 250,000 people with agricultural land to the north and an estuary with some kind of coastal defences, which might be typical of a city of that size. We asked, we had a range of attendees at the workshop who were, for example, consultants or kind of climate change specialists or coastal planners. So we presented them with this location. We asked them what defences they thought might be in place. We presented the available information on future sea levels for this location, so the information from UK CP18 to 2300. We asked the attendees to consider what decisions they might make across the whole time horizon. And then in 10-year increments, we asked them what decisions they might make over those 10 years. And at the end of those 10 years, we asked them to talk about whether they thought they made the right decisions. So yeah, they were kind of thinking in terms of like what flood risk plans might be in place, what defences might be in place, for example. And this kind of helped us to understand the kind of real-time decision making. So just an example as well. Yeah, in this workshop, this is an example information card of the information that we showed. And this kind of, yeah, it kind of helped us understand how the decisions might change kind of in the earlier time horizons, as well as the kind of later time horizons, and how different kind of flood risk management approaches might be explored. So we're also using the storylines approach to develop an update to the existing H++ scenario. So this update would not be in the form of a single scenario or a single projection or range, but more of a dynamic framework, which allows decision makers to explore sensitivities to high-end sea level rise and also explore different sea level rise storylines to understand kind of how the robustness of different adaptation measures stands up. And then we've also kind of found that the decision gaming workshop that we held could be a really complementary tool to this process to allow people to explore this kind of high-end sea level rise space. But it's kind of, I guess, as the sea level kind of science is rapidly evolving, it's kind of important to not just abandon kind of existing assessments, but to kind of reflect and review and see whether these should be updated. Yeah, and also we've been looking at the Met Office how sea level rise storylines also explore also affect UK coasts. So working with Fathom to explore and kind of feed these storylines into flood inundation modelling. So this is an example image from James Savage, who works at Fathom. And yeah, this will be kind of useful for understanding the impacts to UK coasts. And as part of kind of understanding the high-end sea level rise risk, kind of monitoring global sea level and also the contributing components, including ice sheet instability, will be a really necessary component over the coming years to understand whether sea levels are rising faster than that projected likely range. So yeah, we've reached the end of our talk. Here are some key messages. So sea levels, they don't change uniformly in time and space. Sea levels will continue to change over the coming centuries, affecting coastal flood risk. There are various methods for projecting future sea levels. The Prophecy tool has enabled our colleagues to generate local sea level information across the world and in different international projects. We're working on a new framework to explore high-end sea level rise for the UK, and it is important to monitor sea level and to develop effective adaptation options. So thank you for listening. Yeah, we're very happy to answer any questions.
Well, thank you very much. We have time for a few questions. And I notice there's, while people are thinking of questions to ask, I thought I'd chip in with one of my own. This is more about policy, really. What's the balance between efforts to mitigate sea level rise as against adaptation to sea level rise? In view of the horrors unfolding across the Atlantic, I'm thinking that the needle might have to move more towards adaptation.
Do you want me to take that one, Jenny?
Yeah, okay.
I think it's a really good question, and I think from our perspective, we need both. We need to both mitigate against any impacts of climate change, whether that be the sea level stuff that we've talked about today, or other factors as well. So increases in temperature and potentials for the heat wave, increases in sort of precipitation and rainfall, and the impacts that might have on flooding. So mitigation is a key one to sort of reduce the potential for that hazard and bring us more in line with the lower emissions scenario. But I think, as I mentioned early on in the talk, adaptation is also essential, because particularly with relation to sea level, because we are committed, regardless of those mitigation decisions we make, we're committed to a certain amount of sea level going forwards, very much focused on the fact that the oceans respond very, very, very slowly to changes in temperature. So we will need to have a think about all of the adaptation options that Jenny presented around the Thames Barrier, whether or not that's appropriate for different regions of the world. As to your question on what balance actually is, that's not really one for the Met Office, unfortunately. We provide all of this advice into central government. We have colleagues that are seconded in that really support in translating this information and making sure that it's understood by our policy colleagues in various different departments. And then they pick that up and work on it. And we work with policy departments, we work with adaptation departments. So the key thing for the Met Office is to make sure that the science is understood by the people making those decisions.
Okay, thank you for that. Right, there's a few questions of appeared in the meantime. I'll take them more or less in order, I think. First one was, are there any public models available? I think this means ones that people can pull in off the shelf and try as amateurs.
So the sea level tool that we talked about is public. It requires people to understand how to code in Python, but that's been made public by the Met Office for people to pick up. But I'll hand over to Jenny to talk about a few others, because I think she's been looking into this in the last year as part of her PhD.
Yeah, in terms of public models, yeah, I guess as I mentioned, the IPCC sixth assessment report projections are available. You can download the data by visiting that kind of interactive portal that's online. But then they also have another framework where you can kind of, I guess, edit and kind of use your own component data sets as well. Other public models, I think, yeah, there's other emerging ones as well. Yeah, kind of maybe incorporating, for example, yeah, kind of different emerging data sets. So, for example, there's a study recently which provided illustrative projections out to 2500. So there's a lot of different studies kind of really yeah, kind of trying to push out the projections and further understand sea level rise on different timescales.
Okay, thank you. There's a question here from Fiona. Can you say more about how the frequency of weather patterns associated with storm surges has changed with climate change?
Yeah, definitely. So I think I mentioned that the weather patterns work I presented is usually an hour-long talk. So we have lots of diagrams and plots that talk about this in more detail. I think the key one here is probably just to mention that there are 30 weather patterns that we use in the Met Office to define the typical climate that we experience. The lower numbers are very much associated with sort of anticyclonic conditions, so the conditions that bring sort of hot, dry weather. And then the higher numbers are typically associated with the big storms that are very much linked to the storm surges. So with the climate change projections and thinking about how the frequency of those patterns are changing, there's a large number of patterns that are increasing in frequency, but there are also a large number of patterns that are decreasing in frequency. So in the context of sort of the storm surge work and looking at very much the coastal risk, the frequency changes in the weather patterns doesn't have very much of an impact on the risk that we see. It's very much dominated by the changes that we see in sea level. That's a much bigger component to the actual downstream risk. But there are changes in the weather patterns as well. So I'm more than happy to maybe share with you, Michael, the academic paper that we wrote up about that, and then it can be shared if possible. Right. I don't know how that works, but I
don't know how it works.
I can share it with our and they can link it somewhere maybe.
Yeah, well, people can perhaps contact you directly if they want to follow that.
Or that, yeah, sure.
There's a question from Roger Moore. Admiralty charts, he says, when I was at sea, used a standardized value at the Newlyn gauge for the datum. What are the 0 points for the projections used this evening? Are you using local tide gauges with 0 defined by a base state, or is there some absolute global 0?
Yeah, so for the projections, we use kind of a baseline time period with which to reference the sea level change. So for the IPCC's fifth assessment report, that was 1986 to 2005. The UK CP18, that was 1981 to 2000. The difference between those two baselines is around 1 centimetre, but we try to correct that when we're comparing. And then for the sixth assessment report, the baseline is 1995 to
So that's the
2042.
temporal baseline. I think he's asking about
Yeah.
a geographical baseline. So you would be talking about changes relative to the local sea level at that particular, the local mean sea level at that particular place.
Geographical.
Oh, I'm
As
sorry.
in, yeah, they are the I understand. We're taking them at the local tide gauge coordinates.
Right. Yeah.
Talking about
you're talking about changes. So actually, you're talking about something relative to a particular place and time, I think is how it works.
Yeah, the sea level projections that we've shown in almost all of the plots that we had have the tide gauge record on there as well. So that's one of the things that we use to validate the projections going forward, especially where there's an overlap between the historical tide gauge records and the starting part of those projections that we have as well. So there's one or two examples where there's a misalignment between those, and it means there's a reason for us to go back and review the projections and see why that misalignment might be there. So using the tide gauge records is a really good point for validation of the projections that we have.
Okay, thank you. So I'm looking at Steve McFarland here. Is there much research on how sea level rise will influence other flooding sources, gravity, drainage, rivers, groundwater, for example, in coastal areas? And if so, can you point it out, please?
So this might be one for Jenny and I to tag team on, but I will start off, and then Jenny, feel free to chip in if you think there's anything else. But I think what you're getting at, Steve, is what we would term compound flooding. So it's when you've got flooding that's caused from two different sources. So the coastal source, but also maybe the fluvial source because of an increase in precipitation, for example. It's a really active area of research. So we have a project in the Met Office at the minute that's looking at exactly this, that's looking at what happens if we've got sequences of storms that might pass over the UK, and then we have a storm surge that coincides with a high river outflow as well in those coastal regions. I'm not sure how much of it's actually published at the minute, just because it is such a new area of research. But there's definitely some really interesting things going on, and maybe I'll set up a call with Michael to do a talk next year, and we can go through that.
Right. A question from Graham Russell. Have we underestimated the risk from surges coupled with big waves? Recent big surges have fortunately coincided with low points in the tidal cycle. In Iowen, the 2-meter surge on the Clyde coincided with neap tides. Even at that, there was coastal damage. So it's waves on top of these surge due to pressure and sea level rise, I think is what he's.
Yeah, so I think it links to my previous point. So whilst before I was maybe talking about the surge and the fluvial river input, there's also the same sort of compound research that's being undertaken at the minute that's looking at surge and waves occurring at the same time, or how a surge might occur on the peak of the tidal cycle as opposed to those low points. So I'd say it's definitely an active area of research. Jenny, I don't know if you wanted to comment further on the surge side from what's going on in your department, but definitely in my team, we're very much looking at this now, and what the potential impacts will be on a variety of different customers. But I don't know from the more sort of like technical science side if there was anything you wanted to comment on.
I'm not actually quite sure. Yeah, I think there's definitely work going on as well on my team, but I'm not quite sure of the details.
All right, so we're just trying to sift through some of these questions. Question from Alejandro Pinto. It's glad to see the new framework for exploratory scenarios, similar to the. Would these include rates of change in the storm component? Did you, and when you did your workshop, did you find any trends in the type of decision or adaptation taken by the attendees?
Yeah, so just on the rates question, so not rates of change in the storm component, but the idea is that, so yeah, they're kind of storylines of mean sea level change, but each storyline would be provided, a storyline in terms of the rate of sea level change would also be provided, which is actually not something that's typically been provided before. And then, and I mean, I guess any kind of future changes in storms could then kind of be explored alongside the storylines. Maybe they could then kind of feed into extreme sea level storylines. And then with the workshop, yeah, I think what was interesting is that as the kind of time progressed, the kind of types of decision changed from more local towards kind of more national strategic planning, and then eventually kind of what they found interesting was kind of we kind of eventually provided more and more information on the kind of the state of warming that we were in and kind of population numbers, and it then kind of moved towards more kind of global scale kind of strategies, I guess. So I guess, yeah, kind of mainly the scale of strategy that was needed. Yeah.
Okay, I'm going to take just a couple more questions. I'm jumping back to one from Mike, which starts off with an obscure reference to a book I read about 60 years ago. So I don't really, but the gist of the question is, where are we? Yes, it was hard to get warnings of sea level rise accepted when looking at very small numbers. But do you think talking about increase or small sea level rise, he says in fractions of an inch in that case, but do you think that talking about increased risks and consequences of storm damage is a better way of getting climate change risks understood by the public?
Yeah, I would say that yeah, in the past, I guess where you kind of notice well the effects of sea level is in extreme sea level, and it's in those it's when it hits the media headlines, and that might be when people start to notice more. And so, for example, it might be an event like that. There might be a storm which has caused, for example, disruption to a railway line. Say, what kind of we saw in Dawlish a few years ago, and then you kind of might get interventions which are more reactive. So I would say that definitely kind of the effects of sea level rise are more recognised through extreme sea levels, and would then be recognised kind of more and more increasingly as the rates of sea level rise increase in the future. I guess, is it a way of kind of getting climate change risks understood by the public? Yeah, that's an interesting point. I think it's hard to kind of convey what a meter of sea level rise at 2100. It's kind of hard to kind of convey what that might mean, but yeah, in conveying in terms of risk might be a useful way, and definitely something that can kind of be explored through like a storylines approach, kind of combining it with those extreme sea levels. Rachel, did you have any more to say on that?
No, I don't think so. I mean, I agree with Jenny. I think from my perspective, the key to like good communication of climate projections is to find the impact that the individual's most interested in. So if that's flooding, work back from flooding to the climate hazards that we're looking at in the Met Office. But if that's something else, then just work through that.
All right. As we've done most of the questions, there's one suggesting that perhaps there's some exaggeration in some of the scenarios, but actually the scenarios present a range. So and the worst case is, well, it could be worse than the worst case in some cases. So, and there's someone asking for...
I can comment on that as well, actually.
Yeah, okay.
Just to say that I guess by using the storylines approach, you can explore different emission scenarios, and then kind of as I guess there's emerging research, kind of a kind of intermediate or lower scenarios, you can kind of explore them through storylines as well. So I think kind of there's it's not typically been possible to have a kind of high-end storyline under an intermediate emission scenario, but that's something that could be explored in the future. And I guess, yeah, something that the sixth assessment report provided is sea level projections in terms of warming levels. So that's also something that could kind of be explored through this approach in the future as well.
Okay, I think this is probably the point at which to wrap it up. Well, thank you very much. And thank you also to all the attendees for their questions. A big thank you to both Jenny and Rachel for giving their time and expertise. The talk will be available to see again on video in a few days' time, probably a week maybe. And to find that, you go to the events page on the RMET-S website. There's a couple of slides, I think. Yes. Just to remind you that if you wish to engage further with the Royal Meteorological Society, you can do that through this newsletter that I mentioned earlier. And also, if you're interested in membership, if you contact the Society, you can do that. So thank you again, both to the speakers and to the audience, especially those who ask questions, and a good night. Thank you very much. Bye-bye.
Thank you.
Thanks, everyone. Bye.
Bye.
Bye.